when they're in the industry there. So it's a good thing we need to fix so that you can go through it.
Excuse me, sir.
Yes.
Group A is ready for presentation.
Okay. Okay, so you
Good morning, ladies and gentlemen. My name is Albert Davis Oduor, and I'll be the one to start off today's presentation for Group A, majorly on lasers. Now, the subject to which I'll predicate my presentation this morning is one that has been pertinent as it has been timeless. It is a subject that has been interrogated by great minds across generations, yet remain unsolved in many quarters. This subject on lasers has spurred so many interest and has been at the center stage of technological advancement till date. Now, laser is an acronym for light amplification by stimulated emission of radiation, as you can see from slide 1. Now, being that I'm not the one managing the slides, I'll ask Emmanuel to proceed to the next slide. The second slide, okay. Now, being a man who is passionate on history, the origin of laser traces back to a paper that was written in 1917 on quantum theory of radiation by a man that I was partially named Sir Albert Einstein. Now, Sir Albert Einstein, in his paper, he introduced the concept of stimulated emission, which we will see is going to be a fundamental principle behind lasers. However, despite Sir Albert Einstein coming up with a suggestion on electrons, on atoms emitting light or photons when placed in a certain environment, the first laser was developed in 1960 by a man known as Theodore H. Maiman at Hughes Research back then in 1960. And this therefore raises question then, what is a laser and how has it been of importance from 1960 when it was first implemented until now? Now, the simplest way of defining a laser would be like a laser is a device that emits monochromatic, coherent, and collimated light through optical amplification. Now, as you can see from the slide, the term monochromatic, coherent, and collimated have been to some point highlighted. The reason as to why I chose to highlight them are because they are the key terms that helps in differentiating lasers from other microwaves and so on. Now, the term monochromatic just simply means that it emits light of a single wavelength, so that we will see that lasers will be identical and they'll be having a single wavelength and frequency. Now, the term coherent will be used to mean that the lasers that will be, the light that will be emitted will be in phase, and that will allow for highly directional beam. And the term collimation is one tool that we are going to look into. Now, unlike microwaves that operate in lower frequencies of about gigahertz, probably as could be mentioned in the first slide, 300 megahertz to 300 gigahertz, we find that lasers operate at a much higher frequency of about terahertz, which is actually a very, very big, a very, very high frequency. Slide 3. Now, just like microwaves, lasers have their unique properties. And these unique properties include, one, we can talk about monochromaticity. Now, monochromaticity means that it emits light of a single wavelength, as I've already mentioned. And then we also have the lasers are also said to be coherent in nature, meaning that they are always in phase with each other. And then they are highly collimated, meaning that their rays are parallel and there is no significant spread as it propagates. Now, this will be very important in us understanding that lasers are highly directional and are of high intensity. Another property of a laser is the high modulation rate. And to some point, people tend to argue about this, but my view would be that when you look in the case of lasers, in optical transmission, there is more of a high data rate of transmission when you deal with lasers. And so to some point, it can be considered to have this property of a high modulation rate. Next slide. Now, permit me to talk about the theory of lasers, how lasers are being formed, and how exactly the first person, Theodore Hetchman, came to come up with this laser and even develop it back in 1960. Now, from someone I had already mentioned, Albert Einstein, we've said he wrote a paper back then in 1917 that was termed the quantum theory of radiation. Now, Einstein suggested that under proper circumstances, an atom could release excess energy as light or when stimulated by light. And if you can remember so well the Bohr's atomic model that we studied in second year in physical electronics, it was clear that an electron can exist in a specific orbit with fixed energy. Now, if you were to look into the diagram that I've attached, you can see that we have an atom. The atom in it has 3 orbits, with the first orbit being a ground state, and then we also have some other orbits. But the key point is that knowing that in this study of lasers, we will be dealing with 2 terms, and these will be very important. One is the ground state, and the other one is the excited state. Now, most of the time, an electron do prefer to stay at a point where it is stable within the orbits. And when an electron finds itself in a low energy orbit, or rather a stable state, that state is called a ground state. And when an electron is forced to move to another upper energy level, or rather orbit, then it is termed to be at an excited state, as you can see. Now, We've said that it can be noticed that the electron can exist in any orbit with discrete energy, and in each case, there is a step up in energy, as I've mentioned below. Meaning that if I am to move from ground state to another upper energy level, then there will be a difference in energy, and most probably that energy, the energy in the subsequent energy level will be higher than the one in the ground state. And therefore, electrons do naturally like staying within the ground state where it is stable. Slide 5. Now, when we assume, because we say that an electron probably loves staying in its natural state, which is the ground state, sometimes this atom containing this electron within this energy level at ground state could be subjected to a photon. What happens when an electron interacts with the photon? Now, if the energy of the photon equals the energy between the two energy levels, then the photon energy is absorbed by the electron, and the electron jumps to the next energy level and then becomes at an excited state. Now, as you can see from there's a nini that was attached there. You can see that we have an electron. We have an atom, kind of identical, and then we have the energy level. There is a ground state. There is an excitation state. Now you can see there is a photon that is interacting with an electron at ground state. Now, because the energy of the photon equals the energy between the two energy levels, the electron will absorb the photon energy and it will make it to jump to the next energy level. Now, it will be noted that this absorption can only occur. This can only occur when the difference in between the energy levels equals the energy of the photon. That's the condition that has to take place. And this type of a process is one that we will term as stimulated absorption. Kindly take note. We will term it as stimulated absorption, the process by which an electron absorbs the energy of a photon and jumps to the next energy level. We will call it a stimulated absorption. And you should also remember that absorption only occurs when energy of a photon equals the energy between the two energy levels. Next slide. Now, due to the fundamental principle of energy minimization, electrons naturally tend to occupy the lowest possible energy. Therefore, at excited state, the electron lifespan is small to nanoseconds. Now, due to the short lifespan and instability that exists within the excited state, the electron does jump back to the ground state and releases an energy equal to the energy of a photon. Now, this can be seen in the two diagrams that I again have. Now, we see that an electron has, the first scenario we had was an electron interacting with a photon so that its energy increases, and therefore it goes to the next energy level, what we termed as stimulated absorption. But now, when it reaches the excited state at that upper energy level, the electron become very, very unstable. And this is because of the fundamental principle of energy minimization, that electrons naturally tend to occupy the lowest possible energy. That is where they are comfortable. Now, when we change the energy level of the electron, we take it to an upper energy level, its lifespan is so short, and it is to a nanosecond. You can just imagine how small that is. And therefore, the electron will be forced to jump back to the ground state. And as it jumps back to the ground state, it will release energy, and that energy that will be released will be equal to the energy that was absorbed while the stimulated absorption was taking place, and that is equal to the energy of a photon. Now, naturally, when you look into the real life, we've seen several instances of this occurring. Mostly, it is called, physicists call it an electron relaxation. But for our case, I'll call it a spontaneous emission. Now, electron relaxation in real life occur in several instances. I know you guys in your homes, you've seen fireflies before. Now, the way in which fireflies emit that light is due to electron relaxation, in the sense that when excited molecules in fireflies, they actually release the energy as visible light. And you always see the fireflies releasing that light. That is a process called bioluminescence. It is kind of a process in which the electrons, the particles within the fireflies, they're excited and then they jump back to their ground state, so that the visible light is being released. Another instance of electron relaxation, for that matter, or rather spontaneous emission, is in fluorescent light, where electrons get excited by electrical energy and then they return to ground state. And when they return to ground state, there is an emission of a visible light. So each and every process that we are dealing with here has its own impact in technological advancement and even naturally in what we see in our daily lives. Now, that is now what we call spontaneous emission, and also called the electron relaxation. Note the two, stimulated absorption and spontaneous emission. Next slide. Now, at times, because we've looked into the two cases, the cases of a stimulated absorption, electron absorbing energy of a photon and jump to the next energy level, and then the electron being unstable at the excited state due to the shorter lifespan and returns back releasing a photon. Now, what happens? What do you think would happen if if the electron that is still at the excited state interacts with another photon? That should be the question. That now, though the lifespan of the lifetime of an electron at the excited state is so short, what happens when it interacts with a photon at such a short time? What do you think will happen? Now, what happens is simple. What happens is that the electron, again, that is already at excited state, will absorb that that photon energy, and during the spontaneous emission, it will release now a double energy, the one that was absorbed to take it to the excited state, and the one that it absorbs at the excited state. So that when there will be two photon energies that will be released in that case. Now, that type of scenario, we will call it stimulated emission. Now, stimulated absorption, spontaneous emission, and stimulated emission are going to be the three key processes that we are going to use in understanding production of lasers in this presentation. Now, what we will notice is that the two for the stimulated emission, we notice that there are two photons that are being released. Now, the two photons that are being released will be said to be coherent, in the sense that the second photon that is being released will have the same wavelength as the first one. And so that is why lasers are being considered coherent. No, they are being considered monochromatic. Now, the coherency comes in the sense that the two photons that are being released are in phase. And that is why we say that lasers are also coherent. Now, that's also important. Next slide. Now, Now, since we've talked about the three processes, stimulated absorption, spontaneous emission, and stimulated emission, there is another very important process that has to be done in production of lasers. And this process is called population inversion. Now, population inversion, okay, like if I was to say that in an effort to produce more photons, because we've seen that stimulated emission, that is an electron at excited state interacting with another photon so that it produces a double photon. We found that here we are only producing 2 photons. But what if we need more of these photon energies to be produced? We will use this thing called population inversion. Now, in an effort to produce more photon, population inversion is going to be used. Now, in normal circumstances, the higher an energy level lies, the less populated it is, right? Because when you look at from ground state and then you increase the energy levels, as you move up, we expect less and less populated energy levels as we move from ground state. Now, you can even see that from the distribution that I have. We have a normal distribution where you can see that in ground state, you have several electrons. But now as you proceed, as you go up further and further from the nucleus, away from the nucleus, you find that the distribution is less populated. Now, population inversion now aims at making the upper energy levels to be more populated than the ground state. Now, we see that under some circumstances, we can have a system that can be constructed so that there are more electrons in that upper energy level than in the normal conditions. And if I could ask, can anyone maybe guess the circumstance in which we can find electron being more in the upper energy levels than in the ground state? I know you guys can guess. But now what happens, the circumstance in which we can have such a thing happening, where we have more electrons on the upper energy levels, is when we have a relatively longer lifetime in the upper energy level. Now, at excited state, we said that the lifetime of an electron was 2 nanoseconds. Now, if we can find a way of increasing the lifetime of an electron in the upper energy level, maybe to a millisecond, so that the electron stays within the upper energy level for a longer time, we will lead to a production of more photons. Now, the upper energy level that will have the upper energy level that will have a longer lifetime, a relatively longer lifetime, will be termed as a metastable state. Now, if we can assume an electron that undergoes stimulated absorption, and then it moves to the excited state. Now, at excited state, it is unstable, as we've said, and with a shorter lifetime, it falls down to a metastable state. Now, I don't know if you guys can visualize what I'm talking about. Now, okay, maybe let me take you to the second figure that I have, the one for population inversion. You can see that there is an inverse in population. There are more electrons. No. There are more electrons in. Who is managing these slides? Yeah, you can see that there are more electrons on the upper energy level as opposed to the one in the normal distribution. Now, I want us to look into the second energy level, the one that has multiple one. I don't know if I can't manage the slide, so I don't know if you can see in population inversion, the middle energy level, you can see it has more electron. Now, let me call that in middle energy level a metastable state. Now, what happens is that when after stimulated absorption and an electron moves to an excited state, Of course, at excited state, that's the one above, the one with 2 electrons, you will find that there is less, the lifetime is so small, and therefore the electron will be forced to jump back downwards to a metastable state. Now, what happens at a metastable state is very, very important. You can move to the next slide. Now, at the metastable state, next slide. Yeah. Hello, are you guys hearing me? Or I'm talking to myself?
Yes, we can.
Yeah.
Yeah, can you see Emmanuel's screen presentation?
Yes.
Okay, thank you. Now, now let us look at what happens at a metastable state. Now, look at the diagram that I have. You can see I have 2 atoms. Now, each atom has a ground state and each atom has an excitation state, but between the 2 states, there is a metastable state. Now, I want to assume that in the first case, you can see that there is an electron that is that had undergone a stimulated absorption, and it went to an excitation state, and there it stayed for nanoseconds. Now the electron, of course, will drop back, and when it drops, it finds another energy level that we call the metastable states. Now, at the metastable state, we found that the electron will tend to have a longer lifetime that is to a millisecond, which is kind of it's kind of longer time than the one for a nanosecond. And therefore, the electron will stay in the metastable state for a while before it drops back to the ground state. Now, when the electron is still at the metastable state, assume it interacts with another photon. What will happen? The electron will absorb the electron will absorb the photon energy, and then when it drops back to the ground state, there will be 2 photons that will be released. Now, because atoms are always closely packed to each other, the 2 photons that are released will find another electron in the metastable state in the second scenario. The 2 photons they will interact with another electron in the metastable state, and what will result is that there will be 3 photon energies that will be produced. Now, you will realize that due to population inversion, so long as the electron is able to stay in a certain energy level for a very long time, and then there is a subsequent increase in interaction between the photon and the electrons, then you'll find that there will be more photon energies that will be released. And this is a very important principle when it comes to lasers. Because what you want is to introduce more and more and more and more of photons. If we can produce more photons, then everything will be okay, and there will be a result in more energy being released. Next slide. I don't want to take more time. Now, you can see that in metastable state, it allows more electron to stay as it has more lifespan. Now, due to population inversion, more energy is released. The radiation released are also in phase, that is, they are coherent. Now, this can also be depicted as shown. You can see in an excited state, the lifetime is to 10 raised to -7 seconds. Probably it's always nanoseconds, and then it drops back. Now, when it drops to a metastable state and interact with another photon, it will produce 2 energies, 2 photon energy. The 2 photon energy interacts with another electron in another atom, and it will produce another multiple of photon energies. Now that will happen for until the milliseconds are over, and there will be production of more energy before it returns to the ground state. Next slide. Now it should be noted that that the emission due to population inversion do occur in different directions, because you find that each and every electron produces a photon in different direction. Now, hence, to ensure that we get a strong focused beam, there is a way at which the laser, that device is being constructed. Now, the construction of a laser as a device is always made up of one. It has two mirrors. Now, one mirror is always highly reflective, and the other one is partially reflective. We will see why. We always have two sources of light that produces what we'll call optical pumping, and we'll also have a laser cavity. Now, to help in making the photons that are being released to not to be in different direction, we will ensure that we have a very strong focus beam. We'll have to apply an energy source through the laser cavity. And then to increase the effect of stimulation, we'll introduce two mirrors, with one being partially reflective, and the components can be shown. Now, what happens within the laser cavity is very, very interesting. And is interesting to the sense that, okay, can you go to the next slide? Maybe I'll, oh, okay, just go to the previous slide. I thought there's something. Now, what's happening is that within the laser cavity, what happens is this. Now, remember that we have produced, within the laser cavity, there is this dielectric that is, or rather a medium. Now, normally it is always an active medium that we have within the laser cavity that has these atoms in them. Now, there is always the energy sources that are being produced along the length of the laser cavities. And then we have two mirrors. One is partially reflective and one is 100% reflecting. Now, what happens is this, that once population inversion has occurred, so that we have multiple energies, multiple photon energies that have been released in different direction. Now we will tend to have them being reflected back and forth between the two mirrors, and this reflection will lead to something that we'll call a standing wave. A standing wave will result within the laser cavity, and when the standing wave results within the laser cavity, there will be resonance. Now, when the beam is strong enough, then it can be released as a laser that is a collimated beam in the partially reflected mirror side. Now, that is something that we are going to see in a few. Next slide. Now, the generalized working principle of a laser involves the three things that we said. We talked about stimulated absorption, a spontaneous emission, and stimulated emission. Now, we say that stimulated absorption is a case where a photon interacts with an electron, and when the photon energy equals the energy of the two energy levels, the electron is forced to move to an excitation state. Next slide. Next slide. Now, there is the spontaneous emission. We say that now, since the lifespan of an electron at excitation state is to a nanosecond, it is again forced to return back. It has to return back to its ground state, and therefore it releases an energy that is equal to the energy of the photon. There's also stimulated emission, where now an electron at excited state interacts with another photon, and what result is two photon energies being released. And then there's also a case for population inversion, the one that we've said. All that is shown below. Next slide. Now, that is the laser cavity. You can see it has a pumping energy. You can see there is a highly reflected mirror, there is a partially reflected mirror, there is a gain medium. Now, what you said is that due to population inversion, there will be several photons that will be produced. Now, the multiple photons will be reflected back and forth, creating resonance, resulting to a standing wave. And that will go on and on until a strong beam is being produced. Now, the beam that is being produced is one that is collimated, and we will understand why it is collimated. Now, during this process, the emission within the laser cavity is in different direction, and so to get a strong focus beam, we have to apply an energy source to the cavity, and the energy source also generates the photons. Now, the two mirrors are then placed to increase the effect of stimulation emission, with one having a highly reflection property and the other partially reflective. The emitted photon energies are then reflected back and forth, creating standing wave of photons at resonance. Now, once the laser beam is strong enough, it is passed through the partially reflective mirror and a collimated beam is emitted. Next slide. Next slide. Now, there's a question I posed there in the previous slide, that what is a collimated beam? I think you guys can now answer that it is that beam that is parallel, meaning that it does not spread significantly as it propagates. Now, the summary of laser production is as shown. You can see we have a laser cavity. We have a laser as a device, let me say so. Within it, it has a gain medium that has an unexcited atoms. Now, when you do an optical pumping, when you allow light to pass through the laser cavity, then it will release photons. And when the photons are released through stimulated emission, next slide, through stimulated emission, then they will be reflected back and forth. Next slide. When stimulated emission has occurred and we have several photons through population inversion, then they will be reflected back and forth. That's what we call the optical feedback. And again, we will have a light amplification, and then there will be that oscillation that results to resonance and also the standing wave. Now, you can see the beam that is being released in F is one that is collimated. You can see that they are parallel to each other, and they can travel for a longer distance without a significant spread as it propagates. Now, that is next slide. Now, that is kind of an information on how lasers are being produced. But now lasers have, being that it has taken a center stage in technological advancement, there are several applications, starting from the health to communication to all this. You guys, I know most of you have tattoos. Now those tattoos are laser. I know that most of you have eye problem. In fact, I think I got a friend who had an eye surgery through all this stuff. They use laser. Now, there's cancer treatment, all that laser, dental thing, those who have teeth problem and so on, those are laser. Another application is in the communication industry, and that is, I think it's in the next slide, where you can see that communication through an optical fiber, You can see an optical fiber, and then there is a laser that is actually propagating through it. And then you can see the next one is how exactly communication occurs through an optical fiber, where we have a transmitter and a receiver. And the one key component that we have in this stuff is always something called it's in fact the third figure that we have in under communication through optical fiber is something called a laser diode. And a laser diode actually its function is to produce this coherent monochromatic and collimated light through a process we call electroluminescence. Now here it deals with electron and hole recombination. That's something that I think you guys understand so well. Now, we also have an application in the application industry. We've seen lasers being used in cutting and also in welding. Next slide. Huyu manager wangu bana. And then we also have defense. In defense and military, there is an application of laser. You can see those two guys. I don't know who they're looking for. Maybe a terrorist. But the lasers can be used in detecting objects and so on, can be used in the military. And also there is an application in spectroscopy that is in the scientific research. Now the final slide. Now, from a man to whom I was later named, the one and only Albert Einstein, he said that science without religion is lame, and a religion without science is blind. You guys can think about that, and thank you for listening to me. Thank you. Any questions?
Yes, I have a question. Thank you for your insightful presentation. Yeah, so I just now change maybe the frequency of operation from so that you get the green laser or red one, and also where does directivity of the laser at what stage do we achieve the directivity? Thank you.
Okay, I think that's a very good question. To my understanding, I'll answer what I know, and what I don't know, I'll give it to our beloved lecturer. Now, to start with directivity, now once we have photons released within the laser cavity, and they actually they propagate, not propagating some way, but they are being reflected back and forth. Now, as they are being reflected back and forth, there will be this resonance that occurs, and a strong beam is a strong kind of wave is going to be produced within the laser cavity. Now, that beam is the one that will be released as a collimated beam in the partially reflective mirror. Now, that is where directivity comes in, that the electrons, the released laser, they are very parallel to each other. In fact, when you look into some properties of laser, you will find that they are being said to have a very narrow line width, because they're always very, very small. Now, that small nature and the small nature and the collimated nature of the laser is the one that makes it to be very, very highly directive. And so that even when you use them in optical communication, in optical fibers, then you find that they are not that much divergent from each other. They don't actually spread so much. So that is where the Nini comes from. Now, come to the green lasers and the red lasers, I don't know if that could be related to the atoms that are being used, or the type of pumping energy that we use. That is subject to interrogation. I actually won't say something past my knowledge and understanding, because lest I'll mislead you guys. Now, that one, beloved professor will answer. So,
Yes, thank you.
okay.
You should allow your very good presentation, Albert, but your team members should help you, because that's a question for the team, not for just the presenter. Because you did research on this, it's expected that is this group work, and then it's presented in class. So we expect that your team members should be able to try and answer that.
Yes, I think they'll answer, but there is one who will be talking about the parametric amplification and even measures. I think in their understanding from that research will help us in understanding that, if I was to say so. They'll answer. They'll answer.
Victor has raised his hand. If you have something to say, you may speak.
For me, I believe that different colors of the lasers are formed by having different wavelengths of the light that is being produced, and that is mainly determined by the energy that you send to the electron. So if you have a certain energy level, then there will be a certain wavelength that the light that will be produced.
Yeah. So where do we put those? Where do we put the molecules in the laser device that produce those wavelengths?
There's something within the laser. We said that we have a medium called an active medium, or rather gain medium. And this is the material that amplifies light, which can either be a gas or even a liquid. In some cases, we have the gas laser that's made of helium or even neon. There are some that are solid state lasers, they are and so on. So they're just within the laser cavity. Hope I did answer.
Yeah. So there was the question whether how you produce different colors for laser. Did you hear me? Was the question about how to produce? Oh yeah, it was that. Yeah, I mean, it's just the light on which you are reflecting from that active material. So that should not be an issue. Just like if you have light and then you put some translucent screen which is blue or green or yellow, that's what you are going to see after the reflection. So that's how you produce them. It's not a big issue, and that's very good presentation. You are eloquent. I can't put a face to this name, but it is interesting that sometimes we don't even know our students until very late, because I think with such eloquence, probably your classmates know. It is good for us to find out such talents earlier in time and see what we can do with them. But that is great. All right, so we proceed with the class rep.
If there are no questions regarding this first presentation, you can go to the next one, measures.
Good morning, guys. I'll be taking you through measures, but I'll be using Timothy's device for presentation. So I'll just go ahead and share the screen and start the presentation from there. Can someone confirm if they can see the screen?
Yeah, Yes, you can.
All right. And am I audible enough?
Yes.
So I'll start the presentation. Masers they are like lasers. They are a precursor to lasers. Before the lasers came into being, the scientists began working on masers, and the first scientists to work on this were these guys I've named here on the screen, but the most notable figure is Charles Townes. Charles Townes and his colleagues in Columbia University even received a Nobel Prize for their discovery and their theories relating to the creation of the first maser. So a maser is a device that produces coherent electromagnetic waves, specifically microwaves, by the same process of stimulated emission, just like the lasers. So it's an acronym for microwave amplification by stimulated emission of radiation. So the principle of emission of microwaves is stimulated emission, and it was coined by Albert Einstein in 1917, as Davis said. Basically, atoms are induced into the excited energy state, and they can amplify the radiation at a frequency equal to the elements of the lacing medium, or the masing medium in our case. So we use a resonant cavity so that the radiation inside the medium, the radiation inside the cavity is amplified, feedback standing waves are created, and after a while, coherent radiation is produced. So I won't go into details because Davis explained these steps, but I'll just be naming them as we go. So modern masers can be designed to generate electromagnetic waves at microwave frequencies, even radio frequencies and infrared frequencies. However, before we come to these modern masers, there's been a very large chunk of history, like a very long step along the way. So the first maser, like the first prototype working maser, was the ammonia maser, and it was invented by Charles Townes. And I mentioned him some slides earlier, and the next slide shows the image of the maser. See how huge it was, and it was big, like so massive, and emitted a lot of heat, had to be operated at 273 kelvins or 0 degrees Celsius. So it required special cooling equipment, consumed a lot of power, and so advancements had to be made going forward. I'll give you some slight differences between masers and lasers. In essence, they're almost similar, but there's some slight differences which are key. First is the masing medium. Masers use microwave or radio frequencies and employ a variety of materials such as gases, hydrogen or ammonia, solids, or liquids. I will come to the types of masers, and you'll see where these things come into play. Lasers, on the other hand, they use visible light or UV light, sometimes infrared light, and also use gases like helium or neon. They could use liquids too, like dye lasers, or solids like ruby as the gain medium. Basically, the gain medium is the medium whose atoms are the ones that generate this emission. Frequency of operation. We know that masers operate in the microwave range, but modern masers can operate in even the radio frequency range, which is lower in the spectrum compared to the microwave range. Lasers, on the other hand, operate at higher frequencies, mostly in the visible light range and the near infrared spectrum, usually about 400 nanometers to several micrometers. Notice that in the microwave range, the wavelengths are much larger compared to the visible light range. So masers have measures operate in a longer wavelength, like sort of range. I'll proceed to the next slide. So here are some common types of measures. The classification mostly is based on the measuring medium, but also the structure and how the radiation, the microwave radiation, is produced. So we have the atomic beam measures, which focus on atoms of the elements, and then we have the, oh sorry, I'll give you an example, 3 examples actually of atomic beam measures. We have the ammonia measure, like the one that was invented by Charles Towns, the image I showed you earlier. And we have the free electron measure and the hydrogen measure. The reason I have highlighted the hydrogen measure is because it's one of the primary measures I'll be looking at, so that I can show you how they operate. It will come in the subsequent slides. We have the gas measures, where the gas used as a mixing medium is rubidium. And then we have liquid dye and chemical laser. We have solid state measures. I'll also be looking at some solid state measures in the subsequent slides, so that you can get an overview of how technologically these things have advanced. The measuring medium is ruby, or we have some strontium, titanium. I will look at that later. And then we have a dual noble gas measure. So all these are examples of measures, and there are many more, but I just highlighted a few key ones. So let's look at the hydrogen measure. The hydrogen measure is used as an atomic frequency standard. So we have to have measurement standards so that time can be relative to some standard and things like that. So the main application of the hydrogen measure is in the atomic clock, and together with other kinds of atomic clocks, this help make the International Atomic Time Standard, or Temps Atomique International, or TAI in French, which is the international time scale coordinated by the International Bureau of Weights and Measures. So it's a very key application of the measure. So yeah, so measure oscillations rely on the stimulated emission between 2 hyperfine energy levels of atomic hydrogen. Basically, we have, as David said, a ground state and the metastable state of the hydrogen atom, and
Benson, are you still speaking?
sorry guys, I've been informed that the presenter lost his connection. So I think I'll just start again. Sorry for the inconvenience. Please confirm if you're with me.
Can hear you.
You can hear me?
Yes.
All right. So which slide set was I before I lost the connection?
The next
What
one
was
after
I?
this one.
The beginning of hydrogen measure.
Yes.
All right. So I'm sorry about losing the connection. The hydrogen measure is an important figure in this technological step of advancement. The major application of this hydrogen measure is in like atomic frequency standards. Together with other atomic clocks, this help make the International Atomic Time Standard, or Toms Atomique International, or TAI in French. It's the international time scale, and it's coordinated by International Bureau of Weights and Measures. So basically, hydrogen measures are used in atomic frequency standards. And coming up with these standards is important because we need a reference for measures, weights. We need to know, for example, that why this set of measurement is referred to as a kilo or a pound, depending on the region you come from. So, yeah, I'll proceed. Meso oscillations rely on stimulated emission between two hyperfine energy levels of atomic hydrogen. What I mean by this is, considering an atom of hydrogen, we have the ground state and the next higher energy level, and the energy difference between these two is what gives the simulated emission. I'll quickly go to the next slide, and this one shows sort of a schematic of the hydrogen measure, and it's actually simple. It has a few components. Starting from down, we have the hydrogen discharge, or sort of the source of hydrogen gas, and then we have a state selector, which is responsible for releasing the atoms of hydrogen, like the respective atoms of hydrogen, because this is an atomic measure. So the measuring medium are the atoms. In this case, the atoms of hydrogen. So we have the aperture, or the entrance of the atomic hydrogen, and then we have this microwave cavity, and in this we have the standing waves, and we have the standing waves, and after that a coherent microwave beam is released. So I'll show you how this thing works in the next slide sets. So first, we need to produce a beam of atomic hydrogen. This is done so by submitting the hydrogen gas at low pressure to high frequency radio wave. So hydrogen gas is produced and is submitted to a high frequency radio wave, and the result of this is we have the atoms of hydrogen entering the aperture. So the aperture is important because it is due to this aperture and the magnetic field that we get the atoms being stimulated so that they can be in the metastable region, or what Davis talked about, the population inversion. So basically, we need to create a population inversion so that we have more atoms in the more electrons of the atoms in the metastable region, so that we have more like the lifespan of these electrons in that region is significantly higher than in the traditional higher energy level, so that the we need more electrons in the metastable region so that they have a higher lifespan, so that if we are using electrical pumping or optical pumping to excite these electrons, they can interact with them much longer than if they were in the higher state, because their lifespan is, like David said, in the nanosecond range. So after passing the aperture and the magnetic field, many atoms of the beam are left in the upper energy level of the transition. From this state, the atoms can decay to the lower state, and some microwave radiation is emitted in the process. It's actually similar to the production of lasers. So the cavity is of high quality factor. So the microwaves inside are confined and reinjected repeatedly into the atomic beam. So the stimulated emission amplifies the microwaves on each pass through the beam. So basically, this combination of amplification and feedback defines oscillation. So there's some oscillation inside, and the resonance inside the cavity is tuned to the frequency of the energy transition of the hydrogen, which is around 1.42 gigahertz. A small fraction of the microwave cavity is coaxial cable and then sent to a coherent receiver, so that some microwave being emitted is radio receiver. I'll show you this coupling in an image, or let me just show you right now before I continue. So this is the coupling, but this is a solid state maser, but I'll just show you the coupling. There's a coupling here to the fiber optic cable, and it's sent to the radio receiver. So that's it. So we know that the signal coming out of the
erection time, right? Yeah. And then
I can't hear you, sorry. Please come again.
I think you can continue. I think someone's microphone is unmuted.
Oh, sorry. Like I was saying, the microwave signal coming out of the maser is weak. It has a very low energy, like picowatts. Sorry, the frequency of the signal it's low, yes, but it's fixed and it's stable. So that's a bit good. So the work of the coherent receiver that we coupled one end of the cavity to is used to amplify the signal and change this frequency. This is done using a series of first lock loops and high efficiency quartz oscillator. I haven't done much research on these, but basically this is how it works. So I'll give you some few applications of the hydrogen maser. And as you can see, the first one on the list is the atomic clocks. So it's used as a primary frequency standard in atomic clocks, ensuring that there's high stability and accuracy in timekeeping. Also, the next one on the list, which is very key in GPS tracking. GPS is Global Positioning System. So also, it's used as a stable frequency reference in GPS satellites, ensuring navigation and timing. We use it in telecoms, also providing frequency standards to synchronize digital communication. We have research. Yeah, masers are used in fundamental physics experiments, majorly in the theories of relativity and quantum mechanics that were coined by Albert Einstein. Also in space missions, it's good for navigation and communication. So if you're in space, masers will enable you to communicate in real time with the base station on Earth. Also in astrophysics, the hydrogen maser assists in measuring cosmic microwave background fluctuations, contributing to our understanding of the universe. So that's it on the hydrogen maser. I'll give you another example, but this time this was an atomic maser. So I'll give you an example of a solid state maser, so that I hope these two applications of these two realizations masers rather will give you a deep understanding on the functioning and the entity of masers. So we have solid state masers, and based on the name, we know that solid state masers, they have a solid as the masing medium. Atoms of this solid are the ones responsible for emitting the microwave radiation. So we have these key characteristics for solid state masers. The medium, we use solids as the gain medium. Common materials include insulators and semiconductors that have been doped with specific ions or atoms to provide the necessary energy levels for microwave applications. So we have a key example is like ruby. That's an example of a solid that's used as a masing or gain medium. Population inversion, as Davis talked about, is also key in this to operate. So notice how these things are almost similar. So for population inversion to be achieved, the electrons of the atoms in this solid we have to have more in an excited state than in the grounded state. So this is typically accomplished through pumping, which can be done electrically or optically. The resonant cavity used is required to establish the necessary conditions for amplification. So the cavity enhances the interaction between the microwaves and the excited states for the solid medium. Also, solid state masers are very efficient and have low noise. So it was an advancement from the atomic masers. This is an image of a solid state maser. Look at how small it is, like very small compared to the first image I showed you. It's miniaturized, in other words. And as a result, it can be used in applications that require like a very small device like mobile communication. So this is an image, construction image of a strontium titanate maser. So in this maser, the masing or gain medium is the strontium titanate like crystal. It's a compound of strontium and titan, and it's doped with pentacene. I'm not a chemist, so if you want, you could research on why pentacene is used. I haven't had much time to go deeper into this, but basically the pumping used is optical, so that the atoms of this strontium titanate so that the atoms can be excited, so that we can have population inversion. The strontium titanate crystal is kept in place by this sapphire support. Sapphire is used so that the atoms cannot directly interact. The cavity material is copper, and then we have a coupling port, so that the produced microwaves can be sent to the radio receiver. Or below, just the plots showing the emission of microwaves. I'll give you a few applications. The major ones are these three. First, in telecoms, like I mentioned, the hydrogen maser. They are used in satellite communications. since they have the ability to operate at specific frequencies and with very high precision. Also in astrophysics, help in understanding the universe, the universe outside our Earth. In research, like I mentioned earlier, so various experiments require measures like quantum optics, condensed matter physics, string theory, and things like that. So we have these advantages of solid state measures over the other ones, over the atomic, the gas, the liquid. So they are generally more stable and reliable. They operate at specific frequencies and with high precision. Also, they can be miniaturized for specific applications, like this solid state measure, very small. Hence, it also can be portable. Also, solid state, the nature of the solid state allows for more robust construction and operation under challenging environments. Also, with technological advancements, these solid state measures can be operated at room temperature, which is nice because as the inventions started coming up, it was very hard to operate them since they require to be operated at 0 degrees, which is so cold. And also the cooling equipment was so expensive. But with technological advancements, these ones can be operated at room temperature, making them convenient. Despite these advantages, there are some limitations. I was only able to find 2, but with deeper research, I'm sure there are more, since for the same operations, lasers are more preferred. So the challenges to achieve the adequate population inversion is more complex in solids and compared to gases, of course. But also in lasers, this problem is there because acquiring the adequate population inversion requires the energy of for example, for optical pumping, the energy should just be the right amount of energy equal to the difference between the energy levels. So to achieve that, it's quite difficult, but it happens. Also, cooling and maintenance of these measures is more demanding depending on the material used. So in summary, we've learned that measures came before lasers. Measures have some similar principal operation to lasers. It's almost similar, only that the main difference between lasers and measures is that lasers emit light, visible light, while measures, their emissions are invisible. Because microwaves, radio waves, they are in the invisible range, while the light, for example, a red laser is visible. Yeah, these things work hand in hand in the various applications I've mentioned, like research, telecommunication, astrophysics, frequency standards, so to make our lives better. And for their efforts, the inventors of the measures received a Nobel Prize. So that's the end of my presentation. I'd like to invite any questions.
Yes, I have a question.
Okay, go ahead.
Yeah, the measures you talked about, the cryogenic cooling, and their operation is similar to laser. So I was wondering, do lasers, well, the first laser maybe to be invented, did it require a similar kind of cooling? And what makes lasers require that kind of cooling system? And why does laser not require that?
On the cooling part, when, for example, in the case of optical pumping, so that Davis used the term stimulated absorption. for stimulated absorption to happen, in the laser part, a photon had to interact with an electron in the ground state, and it's stimulated and jumps to the next higher energy level, right? And another photon comes in and interacts with this one as it drops to the ground state. And you know that in this case, the light photons are emitted, but it's not only the light photons, because there's some energy difference, and this energy has to be emitted in some other way. So most of the time, the energy emitted is heat, like the energy dissipated is in form of heat. So imagine if one atom can produce this packet of heat. So a small piece of, I wanted to use mole, but I want to dive into chemistry. A small piece of solid or gas has some atoms. So because this many atoms can produce significant levels of heat, and considering how the first ammonia measure was so huge, a lot of heat was dissipated in the process. So it required operation at 0 degrees or 273 kelvins for those who are used to that sort of measuring standard. And a lot of heat was, so to mitigate the heat, being used at 0 degrees Celsius helped in that regard. But lasers, because of technological advancement, don't emit as much heat. So yeah, that's one advantage they have. So they don't require like cooling facilities as much as lasers. Does that answer your question?
Yes, it does. Could you kindly, if time allows, just explain to me the operation? You had the diagram where there was a cavity, and I think maybe I lost my internet. I didn't quite.
Oh, okay. Okay, so basically, I think this is the image you are referring
Yes.
to. Yeah. So in this image, we can see that we have a hydrogen discharge at the bottom. Can you see that?
Yes.
Yeah. So it's a hydrogen source, like a source of hydrogen gas. But for this thing to work, we require atoms of hydrogen, because this is an atomic measure. Notice that the measuring medium are atoms of hydrogen. But in the universe, like hydrogen occurs as molecules, like hydrogen gas, not like independent hydrogen atoms. So we sort of need to separate these hydrogen atoms so that they can be used independently. Hence, we have a state selector. Is that okay up to that point?
Yes.
Yeah. So after the state selector, we need the atoms of hydrogen to enter the cavity in excited state, so that we can have population inversion, like more electrons of hydrogen atoms in the higher level, so that when this in this case I was using optical pumping to excite the electrons by use of light. So when the electrons is dropping to the ground state, and these light photons interact with these electrons, the microwave emission is generated. So we need this atomic hydrogen to enter the cavity while in the excited state, so that these emissions can happen, so that it can be more effective. So that was how it operates. So to produce atomic hydrogen, the gas is submitted at low pressure to a high frequency radio wave. So this occurs at the hydrogen discharge. And then the state selector will give you population inversion. And then we pass these atoms at the aperture, and we and the magnetic field around it will result in these atoms being excited, so that we have electrons in the higher energy level than electrons at the ground state. This was explained by Davis, so I hope you followed that. Yeah, so that was it. And then as atoms decay, as the electrons fall into the ground state, the microwave radiation is emitted. Basically, that was it. I hope you understand now. Whatever happens inside the cavity is the same as what happens in the laser.
Yes, it's now clear. Thank you.
All right. Any other question? If there's no other question, I'll like to invite, I think it's Emmanuel who's presenting the next topic on parametric amplifiers. I hope time allows. Thank you for your time and for listening and for the questions.
A very good presentation. Victor, you have a question?
Just comments. I think Sam and also Benson also mentioned about the heat generation in the lasers and the mesas. And I was also researching and I saw that due to the law of conservation of energy, the efficiency of the laser or the mesa is not always 100%. So some of the heat does get dissipated, some of the energy gets dissipated as heat. And then also for lasers, they do not produce as much heat, but that is because most of them are pulsed. They don't really operate continuously each second. Some of them do have some small gaps, even though the gaps are nanoseconds. That allows for, it doesn't cause excessive heating, you know, as the amplification constantly occurs. If if it was continuous wave operation of the laser, then the heat produced will be excessive. So at times the lasers are pulsed so that they have less heat generated and therefore will require less cooling as compared to the mesas.
Okay, that's important. And also, in fact, for the mesas, remember the cavity that you're seeing there is a microwave cavity. So what happens there in a microwave cavity? You want to produce this mesa at a certain frequency. So it means that you tune that cavity as a resonant circuit. So when there's resonance with high quality factor, you are going to form standing waves within that. Actually, it becomes a microwave cavity like an oven. So with the standing waves and you keep on injecting that energy, what happens? The energy builds inside there and is supposed to be sent back to be reinjected into at the source of the hydrogen atom. So that is what actually causing that buildup of energy, which would then dissipate as heat within the cavity. All right. Today we have had teachers, not lecturers. You have decided that these students are not going anywhere else after your presentations, except those who didn't come to class. You guys have decided to teach, actually, and that is nice. You have 25 minutes. Parametric amplifiers, I think you will be having too much for the laser and mesa. So I would like to end the class here so that I also join Senate a bit. You guys are supposed to have election, so we have a special